Hello, and welcome to Slience. It is wonderful to have you here with me tonight. Perhaps the world felt a little too loud today, or perhaps you simply enjoy drifting off to a story about the natural world. Whatever brought you here, know that this time is entirely yours. You have finished everything you needed to do. Now, you can simply let go. Allow your shoulders to drop. Let your breathing find a slow, steady rhythm, and feel the comfort of your bed rising up to support you. Tonight, we are tuning into the quietest frequency of the earth. We are exploring the science of winter. It is a season that commands the world to slow down, to rest, and to reset. But within that stillness, there is a fascinating world of activity. We will look closely at the architecture of ice, the way light dances across the tundra, and the clever methods nature uses to stay warm. We will wander through facts about hibernation, the physics of frozen lakes, the crisp clarity of the night sky in January, and many other interesting facts. Everything we talk about tonight is designed to be gentle and calming, a collection of truths about our planet's cold slumber. Some of these facts might be new to you, or they might just serve as a peaceful backdrop for your dreams. And just before we step into the snow, if this calm exploration helps you relax or helps you fall asleep, please consider liking and subscribing to the channel. It helps other people find this quiet space too, one drowsy soul at a time. Now, let's begin. Let us begin our journey by looking at the very architecture of the season itself. Winter is not merely a drop in temperature, but a grand celestial event rooted in the movement of our planet through the cosmos. The year-official start of astronomical winter in the Northern Hemisphere is marked by the winter solstice. This event usually occurs on December 21st or 22nd. It is the day with the shortest period of daylight and the longest night of the year. The word solstice comes from the Latin word sol, meaning sun, and sistere, which means to stand still. For ancient observers watching the sky, the sun's daily path across the horizon appeared to pause on this day, stopping its southward journey before slowly reversing direction to head north again. It is a moment of cosmic stillness that mirrors the quiet rest we feel down here on Earth. This long darkness and cooling air are not caused by our distance from the sun, which is a common misconception. The true reason for winter is the tilt of the Earth. Our planet does not spin perfectly upright relative to its orbit around the sun. Instead, it leans at an angle of roughly 23.5 degrees. During the winter months, the northern hemisphere is tilted away from the sun. This lean means that the sunlight which does reach us hits the atmosphere at a shallow, slanted angle. The energy is spread out over a larger area, making it less intense and unable to heat the ground as effectively as direct summer rays. It is this geometry, rather than distance, that ushers in the cold. In fact, there is a fascinating paradox regarding our distance from the star that warms us. During the height of winter in the northern hemisphere, specifically around early January, the Earth reaches the point in its orbit where it is actually closest to the sun. This point is called the perihelion. At this moment, we are about 3 million miles closer to the sun than we are in July. Despite being physically nearer to the heat source, the angle of our planet's tilt overrides this proximity, keeping the north locked in ice and snow. It is a reminder that in nature, subtle shifts in perspective and angle can matter more than raw power or proximity. Because we are closer to the sun during winter, the Earth actually moves faster in its orbit during this season. According to Kepler's laws of planetary motion, a planet travels more quickly when it is nearer to the star it orbits. So, While the days may feel long and the nights interminable, we are hurtling through space at a slightly greater speed in January than we are in the lazy heat of July. Specifically, Earth travels at roughly 19 miles per second, speeding up just a fraction as it swings past the sun in the winter months. We are racing through the dark, even if the world outside your window feels frozen in time. While astronomers wait for the solstice to declare the start of the season, meteorologists have a different method that is perhaps simpler to follow. Meteorological winter begins strictly on December 1st and ends on the last day of February. This definition is based on the annual temperature cycle and the calendar, rather than the position of Earth in space. By organizing the seasons into full months, it becomes much easier for scientists to calculate climate statistics and track weather patterns over decades. So depending on who you ask, the winter season has two different starting lines, both valid and both marking a shift toward the cold. Once the cold settles in, we often see a delay in the true deep freeze. This is known as seasonal lag. Even though the solstice in December marks the time when we receive the least amount of sunlight, the coldest days of the year usually do not arrive until January or February. This is because the Earth, particularly its massive oceans, holds on to heat accumulated during the summer and fall. It takes a long time for the ground and water to release that stored energy and cool down fully. Just as it takes time for a pot of water to boil, it takes time for the planet to cool, meaning the darkest days are rarely the coldest ones. When the temperature finally drops enough for precipitation, we witness the birth of snow. Snowflakes begin their journey high in the atmosphere, often starting as something much smaller than a drop of water. They begin as water vapor, a gas, which transforms directly into a solid ice crystal without ever becoming liquid water first. This process is known scientifically as deposition. It is a graceful shortcut of physics, where the air simply becomes too cold to hold its moisture as a gas and instantly crystallizes into a solid form, skipping the fluid phase entirely. For this crystallization to happen, the water vapor needs a partner. Every single snowflake you have ever seen, from the largest fluff to the tiniest speck, formed around a microscopic nucleus. This is usually a tiny particle of dust, a grain of pollen, or even volcanic ash floating high in the stratosphere. This tiny imperfection provides a surface for the water vapor to latch onto. Without this microscopic heart, the water vapor might remain as a supercooled cloud, even well below freezing. The beauty of a winter storm is effectively built upon dust, transforming the debris of the atmosphere into sheets of pristine white. Once a snowflake finds its tiny dust particle to cling to, it begins to grow. The shape it takes is dictated by the fundamental chemistry of water. A water molecule consists of one oxygen atom and two hydrogen atoms. When these molecules bond together as they freeze, they naturally arrange themselves into a six-sided lattice structure. This hexagonal geometry is why snowflakes almost always have 6 sides or 6 points. It is a rule written into the atomic fabric of the universe that manifests as a 6-pointed star falling from the sky. The angle of the bonds between hydrogen and oxygen dictates this shape, ensuring that even in the chaos of a storm, there is perfect mathematical order. As the crystal falls through the clouds, it encounters different temperatures and humidity levels. These changing conditions act like a sculptor's tools. If the air is dry and very cold, the snowflake will likely be a simple, flat plate or a prism. If the humidity is high and the temperature is just below freezing, intricate, lacy branches called dendrites will form. This journey through Varying layers of the atmosphere is why the old saying is true that no two snowflakes are exactly alike. Since every flake takes a slightly different path to the ground, experiencing a unique sequence of humidity and temperature, its final shape becomes a unique record of its descent. The man who first proved this immense variety was a farmer named Wilson Bentley, who lived in Vermont in the late 19th century. He was affectionately known as Snowflake Bentley. He spent years standing in the freezing cold, catching falling flakes on black velvet and photographing them through a microscope before they could melt. In 1931, he published a book containing over 2,000 photographs of snow crystals. His work revealed for the first time that these fleeting specks of ice were actually intricate masterpieces of design. He famously called snowflakes tiny miracles of beauty and expressed a sadness that this beauty vanished so quickly when it melted. When these tiny miracles pile up on the ground, they create a profound silence. You may have noticed that the world sounds different after a heavy snowfall. It feels hushed and muffled, as if someone has turned the volume down on the entire neighborhood. This happens because fresh, fluffy snow is very porous. It is filled with tiny air, pockets between the ice crystals. These gaps trap sound waves, preventing them from bouncing off the hard ground. Instead of echoing, the sound is absorbed into the snowpack. A thick blanket of fresh snow can absorb more than 60% of sound energy, creating that distinct, peaceful quiet that defines a winter walk. This quietness is matched by an intense brightness. Snow has a very high albedo, which is a scientific term for how much sunlight a surface reflects. While soil or asphalt might absorb most of the sun's energy, fresh snow reflects up to 90% of the sunlight that hits it. This is why a sunny day after a snowstorm can feel dazzlingly bright, sometimes requiring sunglasses even in the depth of winter. This reflection plays a crucial role in regulating the Earth's temperature. By bouncing solar radiation back into space, vast snow-covered areas like Antarctica and the Arctic help keep the planet cool, acting as a giant shield against the sun's heat. There is a specific name for the smell of impending snow. Even before the flakes begin to fall, many people claim they can smell snow in the air. Science suggests this is due to a combination of atmospheric factors. As the air cools and humidity rises before a storm, our olfactory senses become more sensitive to dampness. Additionally, trace amounts of ozone and nitrogen dioxide in the atmosphere are pushed down to ground level by the falling air pressure. This creates a crisp, metallic, and clean scent that our brains have learned to associate with the arrival of winter weather. It is a biological forecast system that links us to the changing sky. Not all water freezes at the exact same moment. In vast bodies of water, like the ocean, the process is slower and more complex than in a puddle. Ocean water contains salt, which lowers the freezing point. While fresh water freezes at 32 degrees Fahrenheit, seawater needs to drop to about 28.4 degrees before it turns to ice. When it finally does freeze, something fascinating happens. The ice crystal structure pushes the salt molecules out, meaning that sea ice is actually much fresher than the water it formed from. This expulsion of salt makes the water directly beneath the ice denser and heavier, causing it to sink and helping to drive the global ocean currents that circulate around the world. In the northernmost reaches of our planet, the indigenous Inuit people have developed a rich vocabulary to describe the nuances of these frozen landscapes. While the popular claim that they have hundreds of words for snow is often exaggerated, their language does possess a remarkable precision for winter conditions. They have specific words for fine powder snow, snow that is good for driving a sled, and snow that has fallen but not yet settled. This linguistic detail highlights how deeply human culture is intertwined with the behavior of winter. To survive and thrive in the cold, one must understand the snow not as a single thing, but as a complex, ever-changing material. Animals, too, have a deep relationship with the snow. There is a term for organisms that thrive in winter conditions: chionophiles. The word comes from the Greek word for snow, chion, and philos, meaning lover. A chionophile is a snow lover. These are not just animals that tolerate the cold, but creatures that have specific adaptations to benefit from a snowy environment. The snowshoe hare is a classic example. Its large, furry feet act like natural snowshoes, distributing its weight so it can walk on top of deep drifts without sinking. This allows it to travel quickly and efficiently across a landscape that would trap a heavier predator, turning the challenging terrain into a safety advantage. While the snowshoe hare bounds across the surface, other creatures undergo a magical transformation to disappear into the white landscape. This ability to change color is triggered not by the temperature, but by the light. As the days grow shorter in late autumn, the decreasing sunlight signals the pineal gland in animals like the ermine and the Arctic fox. This gland suppresses the production of melanin, the pigment that gives fur its brown or gray color. As the old dark coat sheds, the new fur grows in pure white, allowing these animals to become ghosts in the forest, perfectly camouflaged against the snowdrifts. It is a biological clock calibrated to the sun, ensuring they are dressed for winter before the first heavy flake even falls. Beneath the feet of these white, coated wanderers lies a secret world that we rarely see. It is called the subnivean zone. This term refers to the open space that forms between the ground and the bottom of the snowpack. Heat radiating up from the earth melts a tiny layer of the snow, creating a roof of ice. Underneath this roof, in the space between fallen leaves and tall grasses, mice, voles, and shrews live in a network of protected tunnels. The snow above acts as a thick insulator, trapping the Earth's warmth. Even if the air temperature outside drops to 20 degrees below zero, the subnivean zone remains at a comparatively cozy 2 degrees Fahrenheit. It is a bustling, hidden city of life, thriving comfortably just inches below the frozen surface. For larger animals that cannot fit into these tiny tunnels, the strategy is often deep, prolonged rest. We commonly call this hibernation, but the science behind it reveals it is much more than just a long nap. True hibernation is a state of drastic metabolic suppression. Consider the Arctic ground squirrel. During its winter sleep, its body temperature can drop below the freezing point of water, a feat known as supercooling. Its heart, which normally beats hundreds of times a minute, slows to a rhythm of barely one beat every few seconds. By entering this suspended animation, the squirrel conserves vast amounts of energy, waiting in a silent, statue-like state until the warmth of spring returns to restart its internal engine. Bears engage in a slightly different form of slumber. Their sleep is not as deep as the ground squirrel's, allowing them to wake up quickly if threatened. However, their biological efficiency during this time is a marvel of nature. A black bear can go for up to 100 days without eating, drinking, or passing waste. Instead of starving, their bodies recycle the nitrogen from their waste into protein, which is then used to maintain muscle mass. While we would wither away without food for months, the bear emerges in spring, often with its muscles just as strong as they were in autumn. It is a perfect, closed, loop system of recycling that keeps them alive through the barren months. Perhaps the most miraculous survival strategy belongs to the humble wood frog. Found in forests across North America, this small creature does not hide deep underground or keep its body warm. Instead, it allows itself to freeze solid. When the ice touches its skin, the frog's liver frantically produces massive amounts of glucose, a simple sugar. This sugar is pumped into the frog's vital cells, acting as a natural antifreeze that prevents the water inside the cells from crystallizing and destroying them. The rest of the water in the frog's body freezes. Its heart stops beating. Its lungs stop breathing. It becomes, for all intents and purposes, a block of ice. Yet, when the spring thaw arrives, the frog warms up, its heart restarts, and it hops away as if nothing happened. Birds that stay behind in the cold, like ducks and geese, face the challenge of standing on ice with bare feet. They solve this problem with a biological engineering feature called the rete mirabile, which means wonderful net. The arteries carrying warm blood from the bird's heart weave closely around the veins, carrying cold blood back from the feet. As the warm blood flows down, it transfers its heat to the cold blood returning up. This heat exchange ensures that the blood flowing into the feet is cool enough not to lose much body heat to the ice, but warm enough to prevent the tissues from freezing. It keeps their core warm while their feet remain functional, allowing them to stand comfortably on a frozen lake for hours. This resilience is found even in the trees that stand watch over the sleeping forest. Deciduous trees, those that lose their leaves, enter a state of dormancy that is similar to hibernation. In late autumn, they withdraw the valuable green chlorophyll and nutrients from their leaves, storing them safely in their roots deep underground. This is why leaves change color. We are seeing the leftover pigments after the green has been salvaged. Once the leaves fall, the tree seals the spots where they attached with a cork, like scar tissue. This prevents precious moisture from escaping during the dry winter months. The tree essentially waterproofs itself, locking in hydration to survive the long, thirsty season when water is locked up as ice. While the maples and oaks stand bare and dormant, the evergreens remain steadfast sentinels of green. These trees, the pines, spruces, and firs, have evolved a different set of tools to handle the winter. Their leaves have been modified into slender needles. This shape drastically reduces the surface area exposed to the harsh wind, minimizing water loss. Furthermore, each needle is coated in a thick, waxy substance called a cuticle. This wax acts like a high-quality sealant, locking moisture inside the needle so the tree does not dry out when the ground is frozen solid. The very shape of a pine tree, conical and sloping, is also a deliberate design of nature. It allows heavy snow to slide off the branches easily, preventing them from snapping under the weight of a winter storm. When that snow lands on a frozen lake, it rests upon one of the strangest anomalies in the universe. Most substances in the known world get denser and heavier as they get colder and turn into a solid. If water behaved like other liquids, ice would be heavier than water. It would sink to the bottom of lakes and oceans, eventually freezing them solid from the bed up, killing everything living inside. But water is different. It reaches its maximum density at 39 degrees Fahrenheit. As it cools further towards freezing, the molecules actually spread apart, forming a crystal lattice that is full of open space. This makes ice lighter than liquid water. Because of this unique quirk of chemistry, ice floats. It forms a protective shield on the surface, insulating the liquid water below, and keeping it warm enough for fish and plants to survive the winter. Above these frozen lakes, the winter sky offers its own spectacular display. You may have noticed that the stars seem brighter and sharper in January than they do in July. This is not your imagination. It is atmospheric science. Cold air cannot hold as much moisture as warm air. In the summer, the humidity creates a thick, hazy blanket of water vapor that scatters light and dulls the view of the cosmos. In winter, the dry, crisp air is incredibly transparent, providing a clean window into the galaxy. The result is a canopy of stars that burn with a fierce, diamond, hard brilliance, allowing us to see fainter stars that would be lost in the summer haze. Dominating this crystalline sky is the most famous of all winter constellations, Orion the Hunter. He is easily recognizable by his belt, 3 bright stars in a perfect row. But hanging from his belt is a fuzzy patch of light that reveals a secret. It is the Orion Nebula, a stellar nursery where new stars are being born right now. Even in the dead of winter, when the Earth feels asleep, we can look up at Orion and see a place of fiery creation, a reminder that the universe is always active, always growing. Following close behind Orion is Sirius, the dog star. It is the brightest star in our night sky. Its intense blue, white twinkling is often more pronounced in winter due to the turbulence in the cold atmosphere, acting like a beacon in the long northern nights. For those living far enough north, the long darkness of winter provides the canvas for the aurora borealis, or northern lights. These shimmering curtains of green, violet, and red are not caused by weather on Earth, but by weather on the sun. The sun constantly sends out a stream of charged particles known as the solar wind. When these particles reach Earth, they are guided by our planet's magnetic field toward the poles. There, they slam into oxygen and nitrogen atoms high in the atmosphere. The collision excites the atoms, causing them to light up like the gas in a neon sign. It is a silent, celestial dance that only becomes visible because the winter provides enough darkness for the faint lights to be seen, painting the cold sky with fire. Sometimes, the ice does not stay in the sky or on the ground, but hangs in the air around us. On very cold, clear mornings, you might witness a phenomenon known as diamond dust. This occurs when the air is so cold that water vapor condenses directly into tiny ice crystals that float near the ground. Unlike snow, which falls from clouds, diamond dust forms near the surface. These millions of microscopic, hexagonal mirrors catch the sunlight, causing the air itself to sparkle as if it were filled with glitter. If the sun hits these floating crystals at just the right angle, it can create sundogs or halos, bright spots or rings of light that appear to stand beside the real sun, creating a ghostly, beautiful illusion in the frozen air. When we look closer at the frost that coats the world in the morning, we find that there are distinct types, each formed by a different dance of physics. The feathery, delicate crystals that you might see coating a blade of grass or a wire fence on a calm, clear morning are known as hoarfrost. The name comes from an Old English word meaning old or gray, haired, because the white crystals resemble an old man's beard. Hoarfrost forms similarly to dew, but instead of water vapor condensing into liquid droplets, it skips the liquid stage entirely. On nights when the heat radiates away from the Earth and the air is still, water vapor touches a freezing surface and instantly builds these intricate, interlocking fern-like structures. It is a sign of a peaceful night, as too much wind would break these fragile formations before they could grow. In contrast, if you see a heavy, white coating on the windward side of a tree trunk or a fence post, you are likely looking at rime ice. Rime ice tells a story of movement and wind. It forms when supercooled water droplets, tiny specks of fog that remain liquid even below freezing, blow against a solid object. The moment they strike the surface, they freeze instantly on impact. Because they freeze so quickly, they trap tiny bubbles of air inside the ice, which gives rime ice its milky, opaque white appearance. It creates a frozen record of the wind's direction, building up distinct layers that point back into the storm, shielding the object behind it. On rare occasions, usually in late autumn or early winter, you might stumble upon one of nature's most ephemeral sculptures, the frost flower. These are not true flowers, nor do they fall from the sky. They emerge from the stems of certain plants, often long after the plant itself has died for the season. When the ground is not yet frozen, but the air temperature drops sharply, the water remaining inside the plant stem expands. This pressure forces the water out through thin cracks in the stem. As this water hits the freezing air, it turns to ice immediately. However, more water keeps being pushed out from behind it, extruding long, thin ribbons of ice that curl and loop around each other. The result looks remarkably like white petals or spun sugar. These ice ribbons are so delicate that the warmth of the rising sun or a gentle touch will cause them to vanish instantly. If you were to stand by a large frozen lake on a day when the temperature is rapidly changing, you might hear the ice singing. As the ice sheet expands and contracts with the fluctuating temperature, it builds up stress that is eventually released as a crack. This sudden fracture sends sound waves traveling through the ice. Because ice acts as a dispersive medium, high frequency sounds travel faster through it than low frequency sounds. To a listener standing on the shore, this separation of frequencies transforms a simple crack into a futuristic, descending chirping sound, often described as a laser blast or a ricochet. It is a phenomenon known as acoustic dispersion, a natural synthesizer playing music across the frozen surface. Beneath that singing ice, the water temperature stabilizes, but above it, human ingenuity has learned to use the snow itself for warmth. The igloo, a dwelling masterfully engineered by the Inuit, relies on the insulating power of trapped air. Snow is mostly air, sometimes up to 95% trapped within the ice crystals. When blocks of dry, compressed snow are stacked to form a dome, they create a barrier that stops heat transfer. Inside an igloo, the body, heat of the occupants alone can raise the temperature to 40 degrees or more above the outside air. The interior walls may melt slightly and refreeze, creating an airtight seal that locks out the biting wind. The shape is also mathematically perfect. It is not a simple hemisphere, but a catenary curve, the shape a hanging chain makes, which distributes tension perfectly so the structure does not collapse under its own weight. In the farthest northern regions, where the sun does not rise for weeks at a time, animals must adapt not just to the cold, but to the darkness. Reindeer possess a remarkable ability to change their eyes to suit the season. In the summer, the tapetum lucidum, the reflective layer behind the retina that helps animals see in the dark, is gold. This color is effective for the constant daylight of the Arctic summer. But in winter, this layer transforms to a deep blue. This change is caused by the collagen fibers in the eye becoming compressed due to increased pressure inside the eyeball during the constant dilation of the long night. The blue color scatters light more effectively, allowing the reindeer to spot predators and food in the deep twilight of the polar winter. This enhanced vision also allows reindeer to see in ultraviolet light, a part of the spectrum that is invisible to humans. In the snowy landscape, white fur and white lichen might blend together to our eyes. But to a reindeer, the lichen, a crucial food source, absorbs UV light and appears black against the snow, which reflects UV light. This contrast makes their dinner pop out clearly against the background. Similarly, the fur of wolves absorbs UV light, making their predators appear dark and distinct against the white drift. It is a superpower of vision, granted by the necessity of survival in a monochromatic world. While reindeer roam the tundra, the black-capped chickadee dominates the winter forests of North America with its memory. These tiny birds do not migrate. To survive, they spend the autumn hiding thousands of seeds in cracks of bark, under leaves, and in pine cones across their territory. This behavior is called scatter, hoarding. What is truly astounding is their ability to remember these locations. During the winter, the hippocampus of the chickadee's brain, the area responsible for spatial memory, actually grows larger. New neurons are generated to help store the mental maps of their hidden food pantries. In the spring, when this intense memory is no longer needed, the brain shrinks back to its normal size. They literally grow a bigger brain to survive the winter. While the chickadee relies on its memory to find food, other small birds rely on a deep stillness to survive the freezing nights. The golden-crowned kinglet is a tiny bird that weighs about the same as a single coin. To endure a winter night, where the temperature drops well below zero, it enters a state known as torpor. This is a temporary, nightly hibernation. The bird finds a sheltered branch and allows its body temperature to plummet, sometimes dropping by more than 10 degrees. By surrendering its warmth and slowing its metabolic rate, the kinglet conserves the energy it would otherwise burn just to stay warm. It essentially turns down its internal thermostat to the lowest setting that sustains life, waiting for the morning sun to wake it up so it can shiver back to life. On the ground below these sleeping birds, the wind sometimes engages in a playful act of creation known as a snow roller. This is a rare meteorological phenomenon that you might be lucky enough to see on a vast, open hill. If the snow is sticky and wet, and the wind is strong, but not too violent, the breeze can pick up a small chunk of snow and roll it along the ground. As it rolls, it gathers more layers, growing larger and larger, much like a snowball rolled by a child. However, because the center is often weaker, it can blow out, leaving a hollow cylinder that looks like a white carpet roll or a donut made of snow. These natural sculptures stop only when the wind dies down or they become too heavy to move, standing as silent monuments to the perfect combination of wind and gravity. When ice grows massive enough, it begins to behave less like a solid rock and more like a very slow river. This is the nature of a glacier. A glacier forms when snow accumulates in one location for so many years that the weight of the new layers compresses the old layers into dense, hard ice. Once this ice becomes thick enough, usually about 160 feet deep, it becomes slightly plastic. Driven by gravity, the colossal weight causes the entire mass to slide slowly downhill. This movement is incredibly slow, sometimes only a few inches a day, giving rise to the phrase glacial pace. Yet, this slow grind is one of the most powerful geological forces on Earth, capable of carving out entire valleys and reshaping mountains over thousands of years. As these massive rivers of ice grind against the bedrock beneath them, they act like giant sheets of sandpaper. They pulverize the rock into an extremely fine powder, known as rock flour or glacial flour. This powder is so light that it does not sink when the glacier melts and the water flows into a nearby lake. Instead, it remains suspended in the water column. When sunlight hits a lake filled with this rock flour, The particles absorb the red and yellow wavelengths of light, but scatter the green and blue. This is why glacial lakes, like Lake Louise in Canada or the lagoons of Iceland, often glow with a surreal, milky turquoise color that looks almost unnatural in its vibrancy. The ice of the glacier itself often appears a deep, striking blue, distinct from the white snow on top. This color shift occurs because of pressure. As the glacier weight presses down, it squeezes out the air bubbles that were trapped between the snowflakes. Normal white ice is full of air bubbles that scatter light effectively, reflecting the full spectrum back to our eyes as white. But when the air is squeezed out and the ice becomes incredibly dense, the crystal structure absorbs the red end of the light spectrum. The blue light, however, has enough energy to transmit through the ice and reflect back to us. So, the deeper and older the ice, the bluer it appears, revealing the immense pressure of time itself. In the southern hemisphere, the ice sheet of Antarctica is so heavy that it has actually altered the shape of the planet. The weight of the ice, which can be nearly 3 miles thick in some places, presses down on the Earth's crust with such force that the bedrock has sunk. If the ice were removed instantly, most of the continent would be below sea level until the crust slowly rebounded over thousands of years. This process of the crust sinking under weight and rising when the weight is removed is called isostatic depression. It is a humbling reminder that even the solid rock of our planet is flexible if enough winter weight is placed upon it. Surviving on this shifting, sinking continent is the emperor penguin, the only animal that stays on the open ice of Antarctica during the bitter winter. To endure temperatures that can drop to 90 degrees below zero, they have developed a cooperative behavior called the huddle. Thousands of males stand shoulder to shoulder, packing themselves into a dense formation to share body heat. But the huddle is not static. It moves. Time-lapse photography has revealed that the penguins move in a subtle, continuous wave. Every 30 to 60 seconds, a bird takes a small step, and that movement ripples through the entire colony. This ensures that birds on the freezing outer edge slowly shuffle toward the warm center, while birds in the center gradually migrate to the edge. It is a fair and constant rotation that allows the entire group to survive. Deep beneath the ice, where the penguins stand, another sound fills the dark ocean. Weddell seals, which remain in the Antarctic waters year-round, are among the most vocal mammals in the ocean. During the long winter darkness, the males sing to defend their territory and attract mates. Their calls are not simple barks, but complex, unearthly trills and chirps that sound remarkably like science fiction, sound effects, or synthesized music. These vocalizations can be loud enough to be heard by a human standing on top of the ice, resonating through the frozen layers from the water below. It is a haunting, melodic soundtrack to the polar night, proving that even in the most desolate environments, life is singing. Back in the northern woodlands, the frozen ground creates a challenge for trees that need to move water. One solution is seen in the paper birch tree. Its white, peeling bark is not just for decoration. The white color reflects the winter sun, preventing the tree from warming up too quickly during the day. If the tree were dark, it would absorb heat, causing the sap to thaw. When the sun set and temperatures plunged again, that sap would freeze and expand, potentially cracking the trunk. By staying cool and reflecting the light, the birch maintains a steady temperature, avoiding the damaging cycle of rapid thawing and freezing. This phenomenon is known as sun scald, and the birch's white coat is its natural sunscreen and thermal shield. The stillness of a winter night is also perfect for observing the moon. In the winter, the moon often appears much higher in the sky than it does in the summer. This is due to the tilt of the Earth. In winter, the northern hemisphere is tilted away from the sun, but this tilt points us towards the full moon, which is always opposite the sun. As a result, the winter full moon climbs high, overhead, casting shorter shadows and illuminating the snow with a bright silver light. This high trajectory means the light passes through less atmosphere than a low-hanging summer moon, making it appear crisp, clean, and incredibly bright against the dark backdrop of space. Even the soil beneath the snow has a unique winter characteristic. In regions where the ground remains below freezing for at least 2 consecutive years, we find permafrost. This permanently frozen ground acts like a time capsule. Because the cold prevents bacteria from decomposing organic matter, plants and animals that die in the permafrost can be preserved for thousands of years. Scientists have found seeds in the permafrost that are over 30,000 years old. Amazingly, when these ancient seeds were carefully warmed and provided with nutrients in a lab, some of them sprouted and grew into flowers. The deep freeze of winter had suspended their life, pressing pause on their biology for millennia, until the conditions were right for them to awaken. In the shadow of the Rocky Mountains, a unique weather phenomenon demonstrates that winter is not always a static, frozen state. The locals call it the Chinook wind, a name that originated from indigenous languages and is often translated as snow eater. These are warm, dry winds that blow down the eastern slopes of the mountains. As the air descends from the high peaks, it becomes compressed by the increasing atmospheric pressure. This compression causes the air to heat up rapidly. A Chinook can raise the local temperature by 30 or 40 degrees Fahrenheit in a matter of minutes. When this warm, dry wind hits the snowpack, it does not just melt the snow into water. It often causes sublimation, a process where the ice turns directly into water vapor, vanishing into the air. A foot of snow can disappear in a single day without leaving a puddle, erased by the invisible warmth of the wind. While the Chinook wind clears the plains, the American bison faces the deep drifts head-on. These massive animals are perfectly built for the harsh conditions of the Great Plains. You may have noticed that a bison has a huge, distinct hump over its shoulders and a massive, low-set head. This is not just for show. That hump is a giant muscle that powers the neck, allowing the bison to use its head as a biological snowplow. They swing their heads from side to side, sweeping away heavy layers of snow to expose the frozen grass beneath. Unlike cattle, which will often stand and wait for the storm to pass, the bison turns to face the wind. Its thick, woolly coat is so well insulated that snow will pile up on its back without melting, proving that virtually no body heat is escaping through its fur. Beneath the hooves of the bison, the seeds of wildflowers and trees are engaged in a waiting game known as stratification. This is a safety mechanism engineered by nature to ensure survival. Many seeds have a hard outer shell that prevents them from germinating too early. If a seed were to sprout during a random warm spell in December, the seedling would be killed by the return of the frost in January. To prevent this, these seeds contain a chemical inhibitor that must be broken down by cold. They require a specific number of hours at freezing temperatures before they are chemically allowed to wake up. The winter cold is not an enemy to these plants, but a necessary key that unlocks their potential, ensuring they only rise when true spring has arrived. Hanging from the eaves of a roof or the branch of a tree, The icicle offers a lesson in fluid dynamics. If you look closely at a long icicle, you will notice it is rarely perfectly smooth. It almost always has a series of ripples or rings running down its length. Scientists were puzzled by this for a long time. Recently, they discovered that these ripples are a universal pattern. No matter how big the icicle is or how cold the air is, the ripples are always spaced about 1 centimeter apart. This is caused by the way the thin film of water flows over the surface of the ice. The water traps tiny pockets of air, which slightly insulate the ice, causing the freezing to happen in waves rather than a smooth sheet. It is a constant mathematical rhythm written in frozen water. Winter is not unique to our planet. If we look outward to our neighbor, Mars, we find a season that is both familiar and alien. Mars has ice caps at its poles, much like Earth. However, the snow that falls on the red planet is not made of water, but of carbon dioxide, commonly known as dry ice. Because of the unique crystal structure of carbon dioxide, the snowflakes on Mars are not six-sided stars. They are microscopic cubes. These tiny, square crystals fall from the thin Martian sky, dusting the red dunes in a layer of dry ice. When the sun returns to the Martian pole, this snow does not melt into a liquid. It sublimates explosively back into gas, creating strange, spider-like patterns on the surface that can be seen by satellites orbiting high above. Back in our own atmosphere, a rare event known as thundersnow can turn a storm into a surreal experience. Thunderstorms usually require warm, rising air to generate the static electricity needed for lightning. This is hard to come by in winter. However, if the air near the ground is warmer than the air high above, and there is strong vertical lift, lightning can occur inside a blizzard. What makes thundersnow so special is the sound. In a summer storm, thunder can be heard for miles as it cracks through the open air. In a snowstorm, the millions of snowflakes act like acoustic baffles, dampening the sound waves. The result is not a sharp crack, but a low, muffled rumble that seems to come from everywhere and nowhere at once, a soft growl hidden inside the falling white curtain. To endure such cold, the human body has its own hidden furnace. We are born with a specialized type of tissue called brown adipose tissue, or brown fat. Unlike regular white fat, which stores energy, brown fat is designed to burn energy to create heat. It is packed with mitochondria, the power plants of the cell, which give it the dark color. For a long time, scientists thought only babies had brown fat to keep them warm since they cannot shiver effectively. We now know that adults retain small deposits of this heater tissue, usually around the neck and collarbones. Exposure to cold weather activates this tissue, causing it to consume sugar from the bloodstream to generate warmth, a biological fireplace that lights up when the temperature drops. In the waters of the North Atlantic, the Greenland shark moves through the darkness with a slowness that defies belief. These sharks are the longest living vertebrates on Earth, with some individuals estimated to be over 400 years old. They live in water that is nearly freezing, which slows their metabolism to a glacial pace. A Greenland shark moves so slowly that it burns very little energy, its heart beating only a few times a minute. This slow motion existence in the deep, cold dark, is likely the secret to their incredible longevity. They are living time capsules, drifting silently through the ocean since the time of the Pilgrims, preserved by the frigid waters they call home. When water freezes in a river or a stream, it creates a unique kind of ice known as frazzle ice. Before a solid sheet forms on the surface, the water becomes supercooled and filled with tiny, disc-shaped crystals. in turbulent water. These crystals mix together to form a slushy, oily-looking mixture that flows like lava. This slush can stick to the riverbed in a phenomenon called anchor ice, or it can pile up on the banks. Fragile ice is fascinating because it shows the transition state of matter, a fluid that is part liquid and part solid, moving with the current until the cold finally locks it into place. It is the visible hesitation of the river before it goes to sleep for the winter. If you look out at the horizon on a very cold, calm night, you might see vertical columns of light stretching upward from streetlights or the moon. These are called light pillars. They are an optical illusion created by the atmosphere itself. When the air is frigid, flat, hexagonal ice crystals can drift slowly downward, floating horizontally like falling leaves. These millions of tiny crystals act like miniature mirrors. They reflect the light from a source on the ground or low in the sky, bouncing it back to your eyes in a vertical streak. It looks as though grand, ethereal spotlights are beaming up into the heavens, but it is simply the reflection of our own world caught in the suspended ice of the winter air. There is a curious puzzle in the physics of freezing that has baffled scientists since the time of Aristotle. It is called the Mpemba effect. This phenomenon suggests that, under certain conditions, hot water can freeze faster than cold water. It seems counterintuitive. Logic tells us that hot water must cool down to become cold water before it can freeze, so it should take longer. However, hot water evaporates faster, which reduces the volume of liquid that needs to be frozen. The heat also creates convection currents that move the water around, potentially altering how the cooling happens. While it does not happen every time, the idea that heat can sometimes be a shortcut to ice is a delightful reminder that nature does not always follow the straightest path. Deep in the polar regions, the ice does more than just reflect light. It keeps a library of our planet's history. Scientists drill miles down into the ice sheets of Greenland and Antarctica to extract long cylinders known as ice cores. These cores are time capsules. As snow falls, year after year, it traps tiny bubbles of air between the flakes. When that snow is compressed into ice, those bubbles remain there, preserving a sample of the Earth's atmosphere from the moment they were trapped. By analyzing the gas in these bubbles, researchers can taste the air from 10,000, 50,000, or even 800,000 years ago. It allows us to read the history of volcanic eruptions, forest fires, and temperature shifts, all perfectly preserved in the frozen archives. In the mountains of Japan, a specific group of animals has discovered a luxurious way to beat the winter chill. The Japanese macaques, also known as snow monkeys, are famous for bathing in natural volcanic hot springs. They are the most northern living non-human primates in the world. To survive temperatures that drop well below freezing, they submerge themselves in pools of water that stay at a toasty 104 degrees Fahrenheit. It is not just about survival, it is about stress relief. Researchers have found that the levels of stress hormones in these monkeys drop significantly when they are soaking in the hot water. They are essentially taking a spa day to relax during the long, cold winter, a feeling many of us can appreciate. A much smaller creature, the woolly bear caterpillar, faces the winter with a more extreme strategy. You might recognize this caterpillar by its fuzzy black and rust-colored bands. Instead of hiding in a warm hole, the woolly bear curls up under a leaf and freezes solid. Its heart stops, its breathing ceases, and its body becomes hard as a rock. It can survive this because its body produces a natural cryoprotectant, a substance similar to antifreeze, which protects its cells from bursting. It can remain in this frozen state for months, In the spring, it thaws out and continues on its way to becoming a tiger moth. In some cases, if the summer is too short, it will freeze again the next winter, living for years as a caterpillar before finally transforming. When we humans step onto the ice to skate, we are relying on a unique property of the surface that is still being debated by physicists. For a long time, it was believed that the pressure of the skate blade melted the ice, creating a thin layer of water to glide on. However, we now know that pressure alone is not enough to melt ice at very low temperatures. The current understanding involves something called surface melting. Even at temperatures below freezing, the very top layer of ice molecules is not locked tightly into the crystal lattice. These molecules vibrate more freely, acting like a quasi-liquid. This incredibly thin, slippery layer exists naturally on the surface of ice, allowing the metal blade to glide effortlessly without friction, creating the sensation of flying. The composition of snow itself varies greatly depending on the temperature. Meteorologists often use a rule of thumb called the 10-to-1 ratio. On average, 10 inches of snow will melt down to equal just 1 inch of liquid water. This is what we call average snow. But if the temperature is very cold, the snow becomes much fluffier and drier. In these conditions, the ratio can change to 20-to-1 or even 30-to-1. This dry snow is filled with air and is very light to shovel. Conversely, if the temperature is near freezing, the snow is wet and heavy, with a ratio of perhaps 5-to-1. This heavy snow is surprisingly dense. A single cubic foot of wet snow can weigh as much as 20 pounds, explaining why the world feels so heavy and grounded after a wet winter storm. While the snow piles up, ladybugs have their own way of dealing with the season. In the mountains, millions of ladybugs will migrate to specific sites, often the same ridges and hiding spots used by their ancestors. They gather in massive clusters, huddling together under rocks or logs in a state called diapause. By packing themselves tightly together, they share warmth and reduce their exposure to the cold wind. This aggregation also serves as a defense. Their collective bright colors and the scent they release warn predators to stay away. They sleep through the winter in a great, silent community, waiting for the first warm breezes of spring to disperse them back into the valleys. Winter is not just a terrestrial event. It is a state of existence for many worlds in our solar system. Consider Europa, one of the moons of Jupiter. It is covered in a shell of water ice that is likely 10 to 15 miles thick. The surface temperature is nearly 300 degrees below zero. Yet, despite this deep freeze, scientists believe that beneath the ice lies a vast, liquid ocean of salty water. The gravity of massive Jupiter pushes and pulls on the moon, creating friction and heat within its core. This internal warmth keeps the ocean liquid under the planetary winter shell. It is a concept that challenges our imagination, a frozen world protecting a warm, potential cradle for life in the dark reaches of space. Back on Earth, the trees in the boreal forests have evolved to prevent their own trunks from shattering in the cold. If the water inside a living cell freezes, it expands and can rupture the cell wall, killing the plant. To prevent this, trees like the paper birch and the aspen undergo a process called glass transition. As the temperature drops, the liquid inside their cells becomes incredibly viscous, like thick syrup. Eventually, it becomes a solid glass rather than a crystal. This vitrified state does not expand like ice crystals do. It allows the cellular machinery to remain perfectly intact, frozen in a suspended, glass-like state until the warmth returns to melt the syrup and restart the flow of life. In the deepest, most silent hours of a winter night, the ground itself can sometimes startle the stillness with a phenomenon known as a cryocism or a frostquake. This occurs when the temperature drops rapidly, sending a sudden freeze deep into the soil. The groundwater held within the earth freezes and expands quickly, putting immense stress on the surrounding rock and dirt. Eventually, the pressure becomes too great, and the rock fractures with a loud boom that can sound like a cannon shot or a falling tree. While it might feel like a small earthquake, there is no tectonic movement involved. It is simply the earth reacting to the cold, snapping under the tension of the expanding ice. These events are most common in the middle of the night when the air is coldest, leaving people to wonder what mysterious giant just stepped on the roof of their house. Beneath the ice of a frozen pond, the painted turtle survives the winter by performing a biological trick that seems almost impossible. Being a reptile, it cannot produce its own heat, so its body temperature matches the near-freezing water. But because the pond is capped with ice, the turtle cannot come to the surface to breathe air. Instead, it breathes through a process called cloacal respiration. The blood vessels around the turtle's rear end are dense and capable of absorbing oxygen directly from the water. However, as the winter wears on, oxygen in the pond runs low. The turtle then switches to anaerobic respiration, surviving without any oxygen at all. This builds up lactic acid in their bodies, which would kill most animals. To counter this, the turtle dissolves calcium from its own shell into its bloodstream to neutralize the acid. It essentially uses its own skeleton as a chemical buffer to survive the season. Not far from the sleeping turtle, the beaver is awake and comfortable inside one of nature's most impressive fortresses. The Beaver Lodge is a masterpiece of winter engineering. In the autumn, beavers pile up sticks and cover them with thick mud. When the winter freeze arrives, that mud turns into a layer of frozen concrete that is impenetrable to wolves or bears. Inside, the lodge remains above freezing, warmed by the body heat of the beaver family. If you were to look at a beaver pond on a cold day, you might see a thin wisp of steam rising from the very top of the lodge. This is the ventilation shaft, a small hole left intentionally open to allow fresh air in and carbon dioxide out. It is a chimney for their underwater living room, signaling that life is cozy and safe beneath the armored roof. While we often think of snow as a weather event, technically speaking, snow is a mineral. According to the scientific definition, a mineral is a naturally occurring, homogeneous solid with a definite chemical composition and an ordered atomic arrangement. Ice fits every single one of these criteria. It occurs naturally. It is solid. It is pure H2O, and it has a hexagonal crystal structure. This means that when you see a snowdrift, you are looking at a pile of sediment, and a glacier is technically a metamorphic rock. Falling snow is literally diamonds of water falling from the sky. A temporary mineral that defines the geology of winter just as much as granite defines a mountain. There are places on Earth, however, where winter does not bring snow at all. The McMurdo Dry Valleys in Antarctica are the driest places on the planet. Here, the landscape is barren, rocky, and free of ice. This is caused by the katabatic winds, fierce gusts that blow down from the mountains at speeds of up to 200 miles per hour. These winds are so dry and powerful that they evaporate any moisture instantly. It is a winter desert that has not seen significant precipitation for nearly 2 million years. The conditions here are so extreme and alien that scientists use these valleys as a testing ground for Mars rovers, as it is the closest environment on Earth to the surface of the red planet. back in our own homes, winter brings a familiar and sometimes startling companion: static electricity. We are all used to the sudden snap of a shock when touching a doorknob in January. This happens because the winter air is incredibly dry. In the summer, the moisture in the air creates a thin, conductive coating on surfaces in our skin, which allows electrons to flow harmlessly away before they can build up. In the winter, that moisture is gone. As we walk across a carpet, our shoes transfer electrons, building up a charge on our bodies. Because the dry air is an insulator, the charge has nowhere to go until we touch a metal object. That spark is a miniature lightning bolt, a visible release of the energy we gathered simply by moving through the dry winter world. If you have ever poked a hole deep into a snowbank with a ski pole, you may have noticed that the light coming from the bottom of the hole is a striking, glowing blue. This is not a reflection of the sky. It is the true color of water. While a single snowflake reflects all light and appears white, a deep pile of snow filters the light. As the sunlight travels through the layers of ice crystals, the red and yellow wavelengths are absorbed by the ice. The blue wavelengths, however, have enough energy to scatter and travel deeper. When that light finally bounces back to your eye, it has been stripped of its warm colors, leaving only a pure, glacial blue. This is the same physics that makes heavy icebergs look like sapphire gems floating in the sea. In the northern forests, there is a bird called the gray jay, often nicknamed the whiskey jack. These birds nest incredibly early, often laying their eggs in late February when the forest is still deep in snow. This seems like a dangerous time to raise a family, but the gray jay has a plan. By nesting in winter, they avoid competition from the millions of migratory birds that will arrive in spring. To feed their chicks, they rely on food they cached away during the autumn. They use their sticky saliva to glue pieces of meat, berries, and insects to the branches of trees above the snow line. This early start means that by the time the other birds arrive to fight for territory, the young gray jays are already grown and independent, having won the race by starting at the starting line of winter. Another master of winter timing is the witch hazel plant. While almost every other plant goes dormant, the witch hazel blooms in the dead of winter or very early spring. Its spidery, yellow flowers curl up when the temperature drops to protect themselves and unfurl when the sun comes out. They are looking for the few insects that are active in the cold, such as winter owlet moths. By blooming when nothing else is, the witch hazel has a monopoly on the pollinators. It is a lonely strategy, but a successful one, providing a splash of bright color in an otherwise gray and white landscape. Even the very length of the day in winter has a profound effect on our biology and the biology of the world around us. This response to the length of day and night is called photoperiodism. It is not the cold that tells a tree to drop its leaves or a bear to hibernate. It is the duration of the darkness. Plants possess a light-sensitive protein called phytochrome that acts as a biological clock. It measures the number of hours of darkness with incredible precision. When the night stretches past a certain critical length, it triggers the chemical signals for winter dormancy. This system is so reliable that even if there is a freak warm spell in December, the trees will not be fooled into budding because the nights are still too long. When we look at the history of our planet, we see that we are actually living in an ice age right now. Technically, an ice age is defined as any period in Earth's history where there are permanent ice sheets at the poles. By this definition, the Quaternary glaciation, which began over 2 million years ago, is still ongoing. We are currently in a warmer phase known as an interglacial period, a brief respite between the major advances of the ice. For most of Earth's history, the planet had no ice caps at all. So, the very fact that we have a winter with snow and ice at the poles makes this a rare and special time in the geological life of our world. High in the mountains of the western United States, a small mammal called the pika spends its summer preparing frantically for the winter. The pika does not hibernate. Instead, it builds a massive pantry known as a hay pile. During the summer, a single pika will make thousands of trips to gather grasses, wildflowers, and sedges. It does not just pile them up randomly. It engages in a process called curing. The pika lays the fresh greens out on sunny rocks to dry them before moving them into its den deep within the rocks. If it stored them wet, they would mold and rot. By drying them first, the pika creates a long-lasting food source, effectively making its own hay. When the snow covers the mountains, the pika sits comfortably in its rock fortress, munching on its preserved summer salad while the storms rage outside. While the pika stays under the rocks, the great gray owl dominates the snowy surface with its hearing. This owl has the largest facial disc of any raptor, a saucer-shaped arrangement of feathers that acts like a satellite dish to funnel sound to its ears. Its hearing is so acute that it can detect the faint rustle of a vole moving under 2 feet of snow. The owl does not need to see its prey. It can hover silently over the white expanse, triangulate the sound, and plunge feet first into the snow with deadly precision. This maneuver, often called a snow plunge, allows the owl to access the hidden subnivean world that protects so many other creatures, proving that even a blanket of snow is no barrier to a master hunter. For those of us observing the weather from the comfort of our homes, the term nor'easter often signifies a major winter event. This name refers to the direction of the wind, not the direction the storm travels. These storms typically move up the east coast of North America from the south. However, because storms in the northern hemisphere rotate counterclockwise, the leading winds that hit the coast come from the northeast. These winds pick up moisture from the Atlantic Ocean and dump it as heavy snow over the land. The unique shape of the coastline, jutting out towards the Gulf Stream, provides the perfect fuel for these systems, making the nor'easter a signature rhythm of the American winter. On a microscopic scale, the transition of water to ice releases heat. It is a strange concept to grasp, but freezing is actually a warming process. As water molecules slow down and lock into a crystal structure, they release energy in the form of latent heat. This is why citrus farmers in Florida will sometimes spray their orange groves with water before a freeze. As the water on the fruit freezes, it releases latent heat, which keeps the fruit inside just barely warm enough to prevent damage. The coating of ice acts as a peculiar heat-generating blanket, sacrificing itself to save the crop within. In the far north, the soil creates its own geography through a process called frost heaving. When water in the soil freezes, it expands and pushes the dirt upward. If this happens repeatedly over centuries, it can create massive geometric patterns on the ground, such as stone circles and polygons. As the soil expands and contracts, it sorts the rocks by size, pushing the larger stones to the edges of the convection cells. The result is a landscape that looks like it was paved by human hands, with perfect rings of stone separating mounds of dirt. These patterned grounds are one of nature's most orderly mysteries, designed entirely by the expansion of ice. There is a specific type of fog that only exists in the freezing cold, known as freezing fog. Unlike normal fog, which is made of liquid water droplets that bounce off objects, the droplets in freezing fog are supercooled. They remain liquid in the air, but the moment they touch a solid object like a tree branch, a power line, or a spiderweb, they freeze instantly. This creates a coating of hard rime ice, encasing the world in a white, crystalline shell. It can turn a chain-link fence into a wall of white lace and make the simple act of walking outside feel like stepping into a frozen cloud. Under the ice of Lake Baikal in Siberia, the world's deepest lake, a unique phenomenon occurs called methane bubbles. As organic matter on the lake bottom decays, it releases methane gas. In summer, these bubbles rise to the surface and pop. But in winter, they get trapped under the thickening ice. As the ice grows downward, it encases the bubbles in layers, creating suspended stacks of white, disk-like pockets frozen in time. These trapped columns of gas create a stunning, three-dimensional visual effect in the clear, black ice, looking like jellyfish or stacks of coins halted in their ascent, waiting for the spring thaw to release them into the atmosphere. For the North American black bear, the winter den is not just a hole in the ground, it is a marvel of thermal efficiency. Bears often choose den sites under the roots of large trees or in rock crevices that face north, allowing snow to pile up over the entrance. This snow acts as an insulator, sealing the warmth in. Inside the den, the bear curls into a tight ball, tucking its nose under its tail to reduce surface area. This position minimizes heat loss. Remarkably, a mother bear will give birth during this hibernation. The cubs are born tiny and blind, and they nurse on the sleeping mother's rich milk for months, growing strong and furry in the dark, warm safety of the den while the mother dozes, barely waking until spring. We often think of the desert as a place of eternal heat, but winter in the desert is a season of profound beauty and cold. Because there is very little humidity in the desert air to hold heat near the top ground, temperatures plummet as soon as the sun sets. It is not uncommon for a desert to be 70 degrees during the day and drop below freezing at night. This extreme fluctuation creates a quiet, crisp winter night where the stars are incredibly bright. Occasionally, snow will fall on the red rocks of places like Sedona or the Grand Canyon. The contrast of the brilliant white snow against the deep rust-colored sandstone is one of the most striking visual palettes in the natural world, a fleeting moment where fire and ice seem to coexist. Even the oceans have their own version of an icicle, but it is far more dangerous. It is called a brinnacle, or the finger of death. In the polar oceans, when sea ice forms, it pushes out salt, creating a super salty, super cold brine that is denser than the surrounding seawater. This brine sinks, and as it descends, it freezes the seawater around it, forming a hollow tube of ice that grows downward like a stalactite. When this icy finger reaches the seafloor, it spreads out, instantly freezing any slow-moving creatures like starfish or urchins in a web of ice. It is a slow-motion, silent trap, a natural mechanism of the deep freeze that creates a sculpture of ice on the ocean floor. On the surface of turbulent rivers or choppy oceans, the cold creates a geometric curiosity known as pancake ice. These distinct, circular disks of ice form when the water is too rough for a single, solid sheet to take hold. As small pieces of slush and ice float on the waves, they constantly bump into one another. This repeated collision grinds down the sharp edges, rounding them off perfectly until they look like white lily pads or pancakes floating on the dark water. Each disc develops a raised rim around the edge, built up from the slush that splashes onto the ice and freezes during the collisions. It is a rare instance where the chaotic energy of the waves works in harmony with the freezing cold to create a perfectly orderly pattern. Along the shorelines of the Great Lakes in North America, This interaction between waves and ice can build structures that mimic the fiery geology of the Earth, ice volcanoes. These form when waves crash with force against the accumulating ice shelf on the shore. The water punches a hole through the ice, and every time a wave hits, water and slush explode upward through the vent. As this water lands and freezes, it builds a cone-shaped mound around the hole. Over time, these cones can grow to be more than 20 feet tall. When they are active, they spout icy slush instead of lava, a cold and quiet eruption that eventually freezes solid when the lake calms down. Far from the lakes, on the windswept tundra, the muskox faces the blizzard with a coat that is an engineering marvel. The muskox possesses an underwool called kiviot, which is one of the warmest natural fibers on the planet. Kiviot is finer than cashmere and is 8 times warmer than sheep's wool by weight. This incredibly dense layer traps heat so effectively that snow does not melt on the muskox's back. To protect their young from the biting wind and predators, the herd forms a defensive circle. They stand shoulder to shoulder facing outward, with the calves tucked safely in the warm center of the ring. It is a living fortress of fur and horn that has allowed them to survive since the Ice Age. In the quiet, damp forests further south, a rare phenomenon known as hair ice decorates the forest floor. You might see what looks like fine, silky white hair growing from a dead branch on the ground. It looks almost like cotton candy or a white wig. For more than a century, scientists were unsure what caused this. It was recently confirmed that a specific fungus is responsible. The fungus is active inside the rotting wood, releasing carbon dioxide and water. When the water is pushed out of the wood pores in freezing temperatures, the presence of the fungus prevents large ice crystals from forming. Instead, the ice is extruded as thin, hair-like strands, each one only about the width of a human hair. These delicate sculptures can last for hours in the shade, but vanish at the slightest touch of sunlight or a warm finger. We often imagine snowflakes as tiny, microscopic specks, but history records a moment when the sky sent down something much larger. In January of 1887, at Fort Keogh in Montana, soldiers and ranchers reported seeing giant snowflakes falling during a storm. They described flakes that were larger than milk pans, with some measuring 15 inches across. While this sounds impossible, meteorologists believe it can happen under very specific conditions. If the air is perfectly still and has high humidity, hundreds of smaller crystals can collide and interlock as they fall. They clump together without breaking, forming a massive, singular aggregate that drifts down like a white parachute. It remains the largest snowflake ever officially recorded in the Guinness World Records. When the snow falls heavily, we often call it a blizzard, but scientifically, a storm must meet strict criteria to earn that name. It is not just about the amount of snow. In fact, a blizzard can happen without any new snow falling at all, known as a ground blizzard. To be classified as a blizzard, the winds must be blowing at 35 miles per hour or more. Furthermore, the visibility must be reduced to less than a quarter of a mile due to blowing snow. Finally, these conditions must last for at least 3 consecutive hours. It is a definition based on the blinding power of the wind, rather than the depth of the drift, marking the difference between a simple snowy day and a true weather event. High above the storms, the winter night sky offers a grand navigation tool known as the winter hexagon. This is not a constellation, but an asterism, a pattern made of stars from different constellations. It connects 6 of the brightest stars in the heavens: Sirius, Rigel, Aldebaran, Capella, Pollux, and Procyon. This massive 6-sided shape dominates the southern sky in the northern hemisphere winter. Inside the hexagon lies the bright red star Betelgeuse, acting as a center point. It is a celestial seasonal marker, a giant jewel box of stars that frames the winter galaxy, guiding the eyes of stargazers on cold, clear nights. Beneath the ice of a frozen pond, the common goldfish and its relative, the crucian carp, perform a chemical magic trick to stay alive. When the pond freezes over, oxygen levels in the water can drop to zero. Most vertebrates would die in minutes without oxygen. These fish, however, switch their metabolism to a process that does not require air. Usually, this process creates lactic acid, which is toxic in high amounts. But these fish have evolved a unique enzyme that converts the lactic acid into ethanol, which is essentially alcohol. The ethanol is then released harmlessly through their gills into the water. In the deepest part of winter, a goldfish is essentially brewing tiny amounts of alcohol to prevent its body from becoming toxic, waiting patiently for the ice to melt so it can breathe again. In the blinding whiteout of an Arctic blizzard, keeping the herd together is a matter of life and death for reindeer. While vision is obscured by the driving snow, the reindeer rely on a unique sound to stay connected. As they walk, a tendon in their knees slides over a bone, creating a distinct, audible clicking sound. This is not a defect, but a biological adaptation. The clicking frequency increases with the size of the animal, allowing the reindeer to hear where their companions are and even how big they are without needing to see them. It creates a rhythmic, reassuring percussion that travels through the storm, a natural metronome that keeps the family moving in unison through the gray and white world. The polar bear, the king of this frozen landscape, is walking a fine line of optical physics. While we perceive the bear as white, its fur is actually pigment-free and transparent. Each hair is a hollow, clear tube. When sunlight hits the fur, it scatters inside the hollow core and bounces back to our eyes, appearing white in the same way a cloud does. Underneath this thick, transparent coat, the polar bear's skin is jet black. This dark skin is excellent at absorbing heat from the sun. The clear fur allows the solar energy to pass through and warm the black skin below, acting essentially like a wearable greenhouse that traps the sun's warmth against the bear's body. On slightly warmer winter days, when the sun softens the top layer of the snowpack, you might see tiny dark specks hopping across the surface. These are often called snow fleas, but they are not fleas at all. They are springtails, ancient microscopic creatures that are harmless to humans. They possess a unique protein in their bodies that is rich in glycine, an amino acid that binds to ice crystals and stops them from growing. This natural antifreeze allows them to thrive in temperatures that would freeze other insects solid. Their jumping ability comes from a tail-like structure called a furcula, which is tucked under their belly and snaps open like a spring, launching them into the air to find new patches of snow. Far out on the frozen Arctic Ocean, a delicate garden blooms on the surface of the new sea ice. These are not plants, but crystal formations known as frost flowers. They form when the atmosphere is much colder than the ice below. Brine, or salty water, is wicked up through porous imperfections in the ice. As this moisture meets the frigid air, it freezes instantly into intricate, fern-like clusters of crystals. These salty ice flowers can cover acres of the ocean, creating a temporary, fragile meadow that looks like lace. They are beautiful but fleeting, as a strong wind or a fresh snowfall will easily destroy the delicate salty petals. The interaction of stone and ice has given rise to the sport of curling, which is essentially a study of friction on a frozen surface. The ice used for this pastime is not smooth like a skating rink. It is pebbled, meaning it is sprayed with water droplets that freeze into tiny bumps. When the heavy granite stone glides over these bumps, the friction melts a microscopic layer of water, allowing the stone to hydroplane. The players sweep the ice in front of the stone to warm the surface and reduce friction even further, allowing the stone to travel farther and straighter. It is a game of thermodynamics, where the manipulation of temperature and pressure guides the stone to its home. In the high mountains, the ptarmigan bird disappears into the winter landscape by molting its brown summer feathers for a pure white winter coat. But its camouflage is only part of its survival toolkit. As winter approaches, the ptarmigan grows dense, stiff feathers on its toes. These act exactly like snowshoes, increasing the surface area of the foot so the bird can walk on top of the soft snow without sinking. When the night becomes too cold, the ptarmigan will fly straight up and dive bomb into the deep snow, burying itself in a powder cave. This snow roost insulates the bird from the wind and the cold air, providing a safe, warm bedroom hidden beneath the smooth surface. Far beyond our own atmosphere, one of the most active winters in the solar system is happening on Enceladus, a moon of Saturn. This small, icy world is covered in a shell of fresh, clean ice, making it one of the most reflective bodies in the solar system. At its south pole, giant geysers erupt from cracks in the surface, shooting plumes of water ice and vapor hundreds of miles into space. This process is called cryovolcanism. The ice ejected by these cold volcanoes actually feeds one of Saturn's rings. It is a moon that is constantly snowing up into space, creating a ring of winter around the giant planet it orbits. Back on Earth, the cycle of freezing and thawing is the engine that drives the production of maple syrup. The sweet sap of the sugar maple tree does not flow because of the warmth alone. It flows because of the fluctuation. During a freezing night, the gases in the tree fibers contract, creating a suction that pulls water up from the roots. During the warm day, the gas expands and creates pressure, pushing the sap out toward the tap. Without the bitter cold of the night, alternating with the gentle warmth of the day, the sap would not run. The sweetness of the syrup is a direct gift of the winter's retreating oscillation, a taste of the season slowly giving way to spring. In the wetlands of Kaish, North America, a plant known as the eastern skunk cabbage begins its year long before the snow has melted. It possesses a remarkable ability called thermogenesis, meaning it can create its own heat. By breaking down starches stored in its massive root system, the plant can raise its internal temperature to nearly 70 degrees Fahrenheit, even when the air outside is freezing. This heat allows it to melt its way up through the frozen ground and the snowpack, creating a small, circular chimney of open air around its purple, hood-like flower. It creates a warm, inviting shelter for the first insects of the Yash season, effectively bribing them with heat to ensure pollination while the rest of the forest is still locked in ice. As the season progresses into February, we look up to see the snow moon. This full moon was named by Native American tribes because the heaviest snows usually fell during this time of year, making hunting difficult. However, the brightness of the snow moon on the white landscape serves a purpose for the nocturnal world. The extra light reflecting off the snowpack allows predators like the wolf and the owl to extend their hunting hours. It illuminates the forest with a ghostly, silver daylight that persists all night long, a time when the boundary between day and night seems to dissolve in the luminous reflection of the winter earth. When the days finally begin to lengthen and the temperature fluctuates above and below freezing, the snow itself changes texture, becoming what skiers affectionately call corn snow. This happens when the snowflakes go through a cycle of melting during the day and refreezing at night. The sharp, delicate points of the crystals wear down, and the snow clumps into large, rounded grains that resemble kernels of corn. This granular snow provides a smooth, velvety surface for skiing, offering a soft and forgiving ride that signals the transition from the powder of deep winter to the slush of early spring. On large lakes, the breaking of the ice can lead to a powerful geological event known as an ice shove. As the ice sheet begins to melt and crack, strong winds can push the massive, floating plates toward the shore. The momentum of the ice is unstoppable. It slides up the beach, piling up into mounds that can reach 30 or 40 feet high, overturning docks, trees, and sometimes even moving cabins. It looks and sounds like a slow-motion tsunami of solids, a grinding, roaring reminder that the ice is moving and the static silence of winter is coming to an end. Deep beneath the soil, the earthworms are stirring from a state called estivation. To survive the frozen ground, earthworms migrate vertically, burrowing up to 6 feet deep to get below the frost line. They coat themselves in a protective mucus to keep from drying out and curl into a knot to conserve moisture. As the ground thaws from the top down, the worms sense the change in temperature and slowly uncurl, beginning their long climb back to the surface. Their return aerates the soil, preparing the earth to breathe again, just as the first rains begin to fall. The very scent of the air changes as the snow recedes, a smell often called the scent of the thaw. This distinct, earthy aroma comes from a compound called geosmin. It is produced by soil bacteria that have been dormant under the snow. As the ground warms and the moisture from the melting snow seeps into the dirt, these bacteria wake up and release millions of tiny spores into the air. This damp, musk-like perfume is the chemical signal to every animal with a nose that the cycle of growth is about to restart. In the final days of the season, we experience a moment known as the equilux. While the Sata equinox is the official astronomical tipping point, the equilux is the day when we actually receive exactly 12 hours of daylight and 12 hours of darkness. It occurs a few days before the spring equinox. It is the moment of perfect balance, the fulcrum upon which the year tilts. The long dominion of the night is finally over, and the sun begins to claim the majority of our hours. It is the silent finish line of winter, a quiet leveling of the scales before the world tips forward into the light. And so, as the balance of light and dark settles, our journey through the frozen world comes to a gentle close. We have traveled from the high atmosphere where snowflakes are born, down to the deep roots of the forest where life waits patiently for the sun. We have seen how the cold is not an empty space, but a canvas for resilience, beauty, and quiet miracles. From the singing ice of the Great Lakes to the silent sleep of the wood frog, winter is a testament to the enduring power of rest. It is the deep breath the earth takes before it begins to sing again in the spring. Now, it is time for you to take your own deep breath. Let the images of diamond dust and sleeping forests fade softly into the background of your mind. There is no more information to learn tonight, no more facts to remember. There is only the comfort of this moment. You are safe, you are warm, and you are sheltered from the cold. Let your shoulders drop away from your ears. Unclench your jaw. Feel the heaviness of your eyelids as they naturally want to close. The world outside can continue its slow, icy spin, but in here, everything is still. Thank you for spending your evening with us here at Slience. I hope these stories of the cold have brought you a sense of warmth and peace. If you found comfort in this journey, remember that this space is always here for you whenever you need to escape the noise and drift into the quiet. Until we meet again, under the stars, let yourself sink deeper into the mattress. Let the darkness wrap around you like a soft, heavy blanket. The night is yours. Sleep well. Sweet dreams. Good night.